Welcome back. Last episode, we handled trig integrals and trig substitution, the techniques that beat square roots and powers of sine and cosine. Today we tackle the last big technique in the Standard Calculus 2 toolkit, partial fractions. The setting is rational functions, a polynomial divided by a polynomial, p of x over q of x. These look algebraic and messy, and a generic rational function has no obvious antiderivative. But there is a remarkable algebraic fact. Every such function decomposes into a sum of very simple pieces. And every one of those pieces is an integral you already know how to do, either a logarithm, a power, or an arctangent. So the strategy is decompose, then integrate piece by piece. Today we'll cover the full 5-step procedure, then work 2 examples end to end. By the end, you'll be able to integrate any rational function on Earth. The strategy in one paragraph. You want to integrate p of x over q of x. There's an algebraic theorem, we'll take it on faith here, that says every proper rational function, meaning the numerator has lower degree than the denominator, can be uniquely written as a sum of 2 types of fragments. First type, a over the quantity x minus a to the k, a constant over a power of a linear factor. Second type, the quantity bx plus c over the quantity x squared plus bx plus c to the m, a linear numerator over a power of an irreducible quadratic factor. The point of the decomposition is that each of those fragments has a known antiderivative. The first type integrates to a logarithm if k equals 1, or a power if k is greater than 1. The second type splits into a logarithm plus an arctangent. Every piece is something you've already seen, so the whole game is find the decomposition, then integrate term by term. The integration is mechanical. The decomposition is where the work is. Step 1. Before anything else, check the degrees. Is the degree of the numerator strictly less than the degree of the denominator? If yes, you have a proper rational function, and you can go straight to step 2. If the degree of p is greater than or equal to the degree of q, the fraction is improper and partial. Fraction decomposition doesn't directly apply. But there's an easy fix: polynomial long division. Divide p by q to get a quotient polynomial s of x plus a remainder r of x divided by q of x, where now the degree of r is strictly less than the degree of q. The polynomial part s of x integrates instantly, term by term, via the power rule. And the leftover r of x over q of x is now proper, so partial fractions applies to it. Long division is the entry ticket. It takes any rational function and splits it into a polynomial plus a proper rational function. From there, it's all downhill. Step 2. Factor the denominator completely. Now, over the real numbers, every polynomial factors into exactly 2 kinds of irreducible pieces: linear factors, the quantity x minus a, and irreducible quadratics, x squared plus bx plus c, with negative discriminant. The discriminant, b squared minus 4c, being negative means the quadratic has no real roots. It can't be split further over the reals. Why those 2 and only those 2? It comes from the fundamental theorem of algebra. Over the complex numbers, every polynomial factors all the way down into linear pieces. Over the reals, the complex roots come in conjugate pairs, alpha plus or minus beta I, and multiplying out the quantity x minus alpha minus beta I times the quantity x minus alpha plus beta I gives a real quadratic with negative discriminant. So the real factorization is linear pieces plus irreducible quadratics from the conjugate pairs. Some factors may repeat. You can have the quantity x minus a cubed or the quantity x squared plus 1 squared. Repetition matters for step 3. Step 3. Write down the decomposition with unknown constants. The pattern depends on the factor. For a single, unrepeated linear factor, the quantity x minus a, you get one term, a over the quantity x minus a, with a single unknown constant. For a repeated linear factor, the quantity x minus a to the k, where k is the multiplicity, you don't just get one term, you get a stack. a1 over the quantity x minus a, plus a2 over the quantity x minus a squared, and so on, up to ak over the quantity x minus a to the k, all powers from 1 up to k, each with its own constant. There are k unknowns from this one factor. For a single irreducible quadratic, x squared plus bx plus c, you get one term of the form the quantity ax plus b over the quantity x squared plus bx plus c. Note the numerator is linear now, not just constant. The rule is that the numerator's degree is 1 less than the denominator's. A quadratic factor needs a linear numerator, 2 unknowns, a and b. Repeated quadratics work the same way as repeated linears, stacked from power 1 up to the multiplicity, each with its own linear numerator. The total number of unknowns always equals the degree of q. That's the bookkeeping check. Step 4. Find the values of all those unknown constants. Multiply both sides by q of x to clear denominators. What you're left with is a polynomial identity. p of x on the left, on the right, a sum of the unknowns times various polynomial pieces. 2 polynomials are equal, as polynomials if and only if they're equal coefficient by coefficient. Method 1. Expand the right side, collect by powers of x, and match each coefficient to the corresponding coefficient in p of x. That gives you a linear system in the unknowns. Solve it. Method 2, often much faster, plug in convenient values of x. If a is a root of a linear factor, the quantity x minus a, then plugging in x equals a makes every term involving the quantity x minus a to a positive power vanish, and typically only one unknown survives. You can read it off directly. This is the heart of Heaviside's cover-up method. In practice, you combine, plug in the linear roots to grab those constants for free, then match a couple of coefficients to finish off the quadratic constants. It's faster than setting up the full linear system every time. Step 5. Once you have the decomposition, you integrate each piece, and every fragment falls into one of three categories. Linear pieces with first power, a over the quantity x minus a, integrate to a times the natural log of the absolute value of x minus a. Linear pieces with higher power, a over the quantity x minus a to the k, with k greater than 1, integrate by the power rule to a negative power of the quantity x minus a, no log appears. The quadratic pieces are the most involved. Given the quantity ax plus b over the quantity x squared plus bx plus c, first complete the square on the denominator. That turns x squared plus bx plus c into the quantity x plus b over 2 squared plus r squared for some positive r squared. Then substitute u equals x plus b over 2, so du equals dx. The denominator becomes u squared plus r squared. The numerator, in terms of u, splits as some coefficient times u plus a constant. Now the integral splits in two. The u part, the integral of u du, over the quantity u squared plus r squared, that's a substitution w equals u squared plus r squared, gives half the log of u squared plus r squared. The constant part, the integral of du over the quantity u squared plus r squared, standard arctangent integral, gives 1 over r times arctangent of u over r. So every piece in the decomposition winds up as a log, a power, or an arctangent. There are no other antiderivatives in the partial fractions universe. First worked example. Compute the integral of dx over x squared minus 1. Step 1, degree check, numerator degree 0, denominator degree 2, proper, no long division needed. Step 2, factor the denominator. X squared minus 1 is a difference of squares, factors as the quantity x minus 1 times the quantity x plus 1. Two distinct linear factors, no repetition, no irreducible quadratics. As simple as it gets. Step 3, write the form. Each linear factor gets a single constant over it. So 1 over the quantity x minus 1 times the quantity x plus 1 equals a over the quantity x minus 1 plus b over the quantity x plus 1, where a and b are our two unknowns. Step 4, clear denominators. Multiply both sides by the quantity x minus 1 times the quantity x plus 1. The left side becomes just 1, the original numerator. The right side becomes a times the quantity x plus 1 plus b times the quantity x minus 1. That's a polynomial identity that must hold for every x. Two unknowns, one polynomial equation. Easy to solve next. Use the cover-up trick. The polynomial identity, 1 equals a times the quantity x plus 1 plus b times the quantity x minus 1, holds for every x, so we're free to pick convenient values. Plug in x equals 1. The b term has the quantity x minus 1, which becomes 0, b vanishes. We're left with 1 equals 2a, so a equals 1/2. Now plug in x equals negative 1. The a term has the quantity x plus 1, which becomes 0, a vanishes. We're left with 1 equals negative 2b, so b equals negative 1/2. Two constants found in two lines. That's the magic of cover-up. Each linear root kills off all unknowns except one. Decomposition complete. 1 over x squared minus 1 equals 1/2 over the quantity x minus 1 minus 1/2 over the quantity x plus 1. Step 5, integrate each piece. Each one is a log. 1/2 the natural log of the absolute value of x minus 1 minus 1/2 the natural log of the absolute value of x plus 1 plus the constant. Combine using log rules, 1/2 times the log of the quotient. Final answer, 1/2 the natural log of the absolute value of the quantity x minus 1 over x plus 1 plus c, one messy-looking rational function converted into a single clean logarithm. That's partial fractions in 2 minutes. Second example, more interesting. Compute the integral of the quantity 3x plus 5 over the quantity x squared plus 2x plus 5 dx. Degree check, numerator 1, denominator 2, proper. Good. Factor the denominator. Discriminant is b squared minus 4ac equals 4 minus 20 equals negative 16, negative. So x squared plus 2x plus 5 is irreducible over the reals. There's no linear factor to split off. The decomposition is just one piece. The whole integrand is already a single fragment of the form, a linear term over an irreducible quadratic, so no decomposition step is needed. We go straight to integration. The technique for that fragment is what we covered in step 5. Complete the square. x squared plus 2x plus 5 equals the quantity x plus 1 squared plus 4. The denominator is now a shifted version of u squared plus 4. Substitute u equals x plus 1. Then du equals dx and x equals u minus 1. Rewrite the numerator in terms of u, 3x plus 5 equals 3 times the quantity u minus 1, plus 5 equals 3u plus 2. Notice the numerator is now already split into a u piece plus a constant piece. That's exactly what we want for the log, plus arctangent split. The integral in u is the integral of the quantity 3u plus 2 over the quantity u squared plus 4 du. Split it. Split the integral into 2 halves. 3 times the integral of u du over the quantity u squared plus 4, that's the log piece, plus 2 times the integral of du over the quantity u squared plus 4, that's the arctangent piece. Log piece first. Substitute w equals u squared plus 4, so dw equals 2u, dw, meaning u, dw equals dw over 2. The integral becomes 3 times the integral of dw over 2 over w equals 3 halves. The natural log of the absolute value of w equals 3 halves the natural log of u squared plus 4. Absolute value drops because u squared plus 4 is always positive. Arctangent piece. Standard form, the integral of du over the quantity u squared plus r squared equals 1 over r times arctangent of u over r. Here r equals 2, so this is 1/2 arctangent of u over 2. Multiply by the 2 out front, and we get just arctangent of u over 2. Add them. The antiderivative in terms of u is 3 halves, the natural log of u squared plus 4 plus arctangent of u over 2 plus c. Back substitute u equals x plus 1. Then u squared plus 4 equals the quantity x plus 1 squared plus 4 equals x squared plus 2x plus 5. Back to the original denominator. And u over 2 equals the quantity x plus 1 over 2. Final answer, 3 halves. The natural log of x squared plus 2x plus 5 plus arctangent of the quantity x plus 1 over 2 plus c. 1 rational function, 1 decomposition, 1 logarithm, and 1 arctangent. The 2 basic antiderivative species of the quadratic case both showing up in the same problem. A quick word on repeated factors, since the examples above didn't have any. Suppose your denominator is the quantity x minus 1 squared times the quantity x squared plus 1. Then the decomposition has 4 terms, a1 over the quantity x minus 1, plus a2 over the quantity x minus 1 squared, plus the quantity bx plus c over the quantity x squared plus 1. 4 unknowns total, and that matches the degree of q, which is 4. The number of unknowns equals degree of q check is a useful sanity test. If it's off, you've miscounted something in step 3. For the solving step, cover-up still works on the highest power repeated linear term. Plug in x equals 1. The a1 term has the quantity x minus 1 to the first power, which vanishes. The quadratic term has the quantity x squared plus 1 fine, doesn't vanish, but it doesn't kill the a2 term. Carefully done, plugging in x equals 1 gets you a2 directly. The others need a matching pass. Integrating the first power term, a1 over the quantity x minus 1, gives a log. The squared term, a2 over the quantity x minus 1 squared, gives a power. No log, just negative a2 over the quantity x minus 1 by the power rule. And the quadratic term gives log plus arctangent. The pattern is robust. Decomposition fragments, when integrated, always produce logs, powers, or arctangents. That's the universe. One reason this technique matters beyond calculus too. In differential equations in engineering, the Laplace transform turns a function of t into a function of s. Linear differential equations with constant coefficients become algebraic equations in S. Solving such an equation reduces to algebra, followed by an inverse Laplace transform to get back to t. And here's the thing, the solutions you produce in the S domain are almost always rational functions. P of s over q of s. To invert the transform, you decompose that rational function by partial fractions, then look up each fragment in a table. Each fragment corresponds to a recognizable time domain function. 1 over the quantity s minus a corresponds to e to the at. 1 over the quantity s squared plus omega squared corresponds to a sine. 1 over the quantity s minus a squared corresponds to t times e to the at, and so on, the same fragments we just learned to integrate. So the partial fractions procedure is doing double duty. In calculus 2, it lets you antidifferentiate a rational function. In differential equations and signal processing, it lets you invert a Laplace transform. Same algebra, 2 applications. You'll see it again and recognize it. 5 practical notes. First, don't forget step 1. Always check degrees before writing a decomposition. Partial fractions only works on proper fractions. Skip long division on an improper one and you'll get nonsense. Second, irreducible quadratic factors get linear numerators, not constants. The most common student error is writing a over the quantity x squared plus 1 instead of the quantity ax plus b over the quantity x squared plus 1. The rule, numerator's degree is always 1 less than the denominator factor's degree. Third, repeated factors need every power, not just the highest. If a factor appears cubed, the decomposition has 3 terms: the first power, the squared power, and the cubed power, each with its own constant. Forgetting the lower powers means the decomposition is incomplete, and you won't be able to match coefficients. Fourth, cover-up is wonderful but limited. It nails simple linear factor constants in one line. For quadratic numerators or repeated factors, you usually need a coefficient, matching pass to finish. Fifth, the universal sanity check. Count unknowns and compare with the degree of Q. They should match exactly. Off by 1? You've missed a term or written one too many. This catch saves time. Recap. 5-step procedure. Step 1, check degrees. Polynomial long divide if needed to get to a proper fraction. Step 2, factor the denominator over the reals into linear factors and irreducible quadratic factors. Step 3, write down the decomposition with unknown constants, 1 constant per linear factor power, 1 linear numerator per quadratic factor power. Step 4, solve for the constants by cover-up or matching coefficients. Step 5, integrate each piece. Every fragment gives a log, a power, or an arctangent. Those are the only antiderivatives that ever appear. 2 worked examples. First, the integral of dx over x squared minus 1 decomposes as 1/2 over the quantity x minus 1 minus 1/2 over the quantity x plus 1 integrates to 1/2 the log of the absolute value of the quantity x minus 1 over x plus 1. Second, the integral of the quantity 3x plus 5 over the quantity x squared plus 2x plus 5 dx, irreducible quadratic, complete the square, split into log plus arctangent. Final answer, 3/2 the log of x squared plus 2x plus 5 plus arctangent of the quantity x plus 1 over 2. With partial fractions, you've now seen the full standard integration toolkit. Substitution, parts, trig integrals, trig sub, partial fractions. Any elementary integral you meet in Calculus 2 falls to one of these or a combination. Next episode, improper integrals. What happens when the interval or the integrand goes to infinity and whether the area is still finite. See you there. That's partial fractions decomposition. If this was helpful, hit like, leave a comment, and consider subscribing. It really does help the channel reach more learners. Post your favorite partial fractions problem in the comments. Bonus points if it has a repeated irreducible quadratic, because those are genuinely painful and great practice. Next episode, improper integrals. We'll define the integral from 1 to infinity of dx over x squared as a limit, watch it converge to 1, and then watch the integral from 1 to infinity of dx over x diverge to infinity, despite looking almost identical to its convergent cousin. Finite areas under infinite curves, infinite areas under nearly identical curves, the paradoxes that motivated rigorous analysis. See you in the next one. With partial fractions in hand, the standard Calculus 2 integration toolkit is essentially complete. Substitution, parts, trig integrals, trig sub, partial fractions. 5 techniques that handle most of what you'll meet in a first course. But there's a stranger frontier. What happens when the interval of integration is infinite? Or when the integrand itself blows up inside the interval? Next episode, improper integrals. We'll define in T1 in f(d)dx x squared as a limit, see why it converges, and watch in T1 in f(d)dx x diverge despite looking nearly identical. Finite area under an infinite curve. The paradox at the heart of analysis. Subscribe. See you there. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.